Welcome everyone. Welcome to the 5th webinar in the series that is co-organized between Europractice and the 2D EPL on graphene. So 3 weeks ago we had a webinar by Graphenia, and today we have the 5th webinar in the series from IHP. So today you will hear a talk from IHP on exploring graphene photonics integration, and more specifically also zooming into the experimental MPW run that is organized by IHP. So before I would like to give the floor to our speaker, Dr. Mindaugas Lukosius, I would first like to give a short introduction to him. So Dr. Mindaugas Lukosius received his Master of Science in Inorganic Chemistry in 2006 from the University of Vilnius in Lithuania. Then he continued to do a PhD in chemistry, which he obtained in 2010 from the University of Oldenburg in the field of CVD depositions and development of high-K MIM capacitors. In 2015, he joined the Graphene Research Group, and since 2018, he's leading the 2D materials teams in the Materials Research Department at IHP. And he focuses on the development and introduction of novel graphene modules into the BiCMOS pilot line. So without further ado, I would like to give the word to Mindaugas, and I wish you all a very nice webinar. Mindaugas, the floor is yours.
Romano, thank you very much for the nice and kind introduction. So today I would like to give you the first details how we explore graphene for the photonic integration. So as Romano mentioned, we are part of the 2D pilot line project, and we are offering this kind of experimental MPW runs. The word experimental comes here also with a meaning that is not that qualified as you can imagine the real MPW services are running. But nevertheless, we make the first steps towards the graphene integration for the MPW services. So here's the outline of my talk. I'm going to briefly introduce IHP. I will briefly speak about 2D materials for the photonic applications and with the specifics of graphene for modulators, where we think has the most potential. And finally, I will give some technical details of what you could expect if you would participate in this experimental MPW run. First information about where I'm coming from. So IHP is a research institute located in east part of Germany, close to the border of Poland, as indicated here. And here are some details listed. I would like you to take two key messages from this slide. That our main mission is to bridge the gap between the basic research and the industries. And for that, we are using 200mm pilot line, and we are doing state-of-the-art BiCMOS technologies, but also the new technologies like graphene technology is also emerging, and we are doing the research on the pilot line scale. To give more details about the clean room, we are around 1,500 square meters, and we are operating 250 and 130 nanometer nodes for the BiCMOS technology. So we are dedicating half of our time to the research and development activities, and half of the time we are developing and dedicating our time for the MPW and prototyping services. So we have 5 departments. So we have the so-called vertical approach, where we can start from the materials in the very early stage. We can apply them in our technology line, and then building the systems out of that, we can provide certain technologies as the services. In this sense, graphene is one of the research topics at IHP, and here is a summary slide what we do with graphene before I go in further details. So as I mentioned, 200mm is the message I want to give here. Standard wafers, what we are doing, and we are solving these kind of technical issues with graphene integration. So we have to grow it, transfer, pattern, passivate, and contact. And once it's solved, we can apply these methods to the fabrication of novel graphene devices. So the scope of today's presentation and the scope of what we are doing with graphene is the photonics. We believe that graphene photonic devices have the potential. And here's an example shown where the graphene modulator, for example, is put on the back end of line of our electronic driver circuit, which is also fabricated at IHP. So this is basically the core of 2D pilot line activities, what we are doing as well. So we really want to make it process development in the large scale. We want to be compatible with silicon technology, so everything what we do and what I am going to discuss is done in our pilot line, which is CMOS pilot line. Certainly, we have to improve and we have to make sure that the devices have sufficient performances. So this is the core activities with the graphene, what we are doing at IHP. But let me start with a very basic introduction of graphene. So I am not going to explain all the details about graphene, but most probably many of you know that graphene can be applied to different application fields, starting from flexible materials in batteries, in head spreading, as well as microelectronic applications. At this point, I would like to mention that, and I would like to define that what I'm going to speak today is a single layer of graphene, as shown in this picture, and it can be grown by CVD. Because I don't want to have a confusion in the literature, many of the works define graphene also as an example shown in this picture. Yes, it can be something banded, it can be a couple of layers and so on and so on. So many of these applications do not require a high quality graphene, single layer graphene, but in photonic applications and in microelectronic applications, so single layer graphene is essential. And whenever I refer to graphene in my talk, I am speaking about a single layer graphene, which is grown by CVD technique. So let's start with electronic applications. And electronic applications are the most advanced ones so far in graphene. Here I just have a couple of examples what can be done with graphene. So for example, the Hall sensors can be fabricated where you have 4 contacts of put it on graphene, and then you can apply a magnetic field, and for example you can monitor the current in the channel. On the other hand, the GFET configuration can also be used for the biosensing applications. And here's an example of the biosensor shown, which is even integrated with the with the CMOS circuits. And this was part of the MPW runs, which were delivered earlier in the project. So there were 4 runs which are already closed, and AMO and VTT have delivered and produced some GFET for electronic applications. And the one that is open now, Romana also briefly mentioned that the webinar took place a couple of weeks ago, and it's still open. So if you are interested in graphene for electronic sensor applications, you can still apply if you're interested and rewatch the webinar on YouTube. What I am interested and what we are interested is certainly the photonic application. So here I collected some of the very brief introduction to the graphene photonics and to D-material photonics applications. So on the left side, we can see the range of materials which can be applied for the modulation, for the modulator applications. On the right side, we are having the applications which are related to photo detection. So we can see very bright spectral range. We can see that these different materials, due to the electronic structure, can be applied at different wavelengths, and various device concepts could be made. So certainly the most important one for us is graphene, and I'm going to talk about this later on. But this shows basically the potential of the 2D materials for the applications in the photonics area. Here I selected to show a couple of examples that even first products or first concepts are being in the market or close to the market. For example, AMO demonstrated some years ago all graphene optical communication link, where the graphene modulator and photodetector is used. A group in Italy, for example, is working on the novel concept of the frequency mixing. 2019, Amberian, for example, launched this photodetector, which is working at various wavelengths. And these are just a couple of examples of the products or device ideas which are realized in the photonics field. Certainly there are much more of them, but I'm just selecting and showing a couple of them in this slide. What's most important and what's most interesting application field is telecommunications. So we all know we want to send and receive data in fast way, and the amount of data which is being sent over the years is increasing dramatically. This is not the latest certainly numbers, but we can assume that the levels of the data that's being sent is increasing significantly. So the core element, the key element of this data communication solutions is the so-called optical fiber, or optical link, or radio link, if you want to name it. And there are two key elements in this optical link. On the one side, we have the modulator. On the other hand, we have photodiode. So these two devices, modulator and photodetector, are the most promising in photonic ones, and there are numbers of works so far, more on the photodetectors than on the modulators. And this shows the potential of the 2D, of the graphene and 2D materials in these two applications. Let me compare state-of-the-art photodetector first of all. So on the left side, I'm showing the germanium photodetector, for example, and I'm showing on the right side the graphene photodetector. And you can see that the 3 dB bandwidth is basically can be defined as a frequency of the information signal when the 3 dB modulation amplitude is applied to the modulator, to the photodetector in this case. And we can see that the bandwidth of higher than 265 gigahertz can be reached with the germanium photodetector, state-of-the-art germanium photodetectors. Very recent paper on the graphene photodetector showing the 3 dB bandwidth of 220 gigahertz. So it shows a nice potential of graphene for the photodetection applications, but there is one significant difference in these two works and reports, that whereas the photodetectors with germanium, for example, they are integrated with BiCMOS, and on the other hand, the graphene photodetector integration is still in the very early research stages. So still a lot of work has to be done. And therefore, in this kind of 2D pilot line projects, we are trying to bridge this gap between the fabrication in the lab and fabrication in the real pilot line. But the scope of today's presentation is where we have the most experience doing that is the graphene modulators. And I would like to give a brief introduction on the graphene modulators. This plot illustrates the way the excitation can be done. So you can see the energy momentum diagram of the graphene, and we can see that we can excite thermally, electrically, optically. And in this case, the x-axis is showing us the speed, how fast it can be done. So we see that the thermally excited modulators are the slowest one. Therefore, electrical and optical modulators are of most importance because they can be quite fast. So just to illustrate the way the electrical modulators are working, the way the electrical signal is then applied. So we have the signal light in our case, which is optical intensity, being constant in the time. And if we apply the electrical command to the optical modulator, we can get the optical intensity out, controlled by the electrical command. On the other hand, if we use the optical modulation scheme, we have the same signal light, but we can send another light source, which we call the modulation light, to the optical modulator, and we can also modulate the signal light with another light source. So therefore, these two approaches are quite interesting and important for our particular graphene modulator applications. Let me explain why. Let me explain why graphene is good for that. And let me start with these three pictures. So let's focus on the middle one. So once again, we are seeing the Dirac cone of the graphene. And in the zero voltage state, let's call it like this, the Fermi level or the chemical potential is somewhere in between these two valence and conduction bands. So it means graphene can absorb the light. As long as we shift the chemical potential up or down by applying positive or negative biases, and once this energy is higher or lower than half of the photon length, we can make the graphene transparent. It means that no light is absorbing anymore in graphene, and therefore we can have 0 and 1 state, if you want to call this kind of principle working. In order to understand this phenomena, we have to go a little bit deeper into the physics. So we have to understand what is the complex refractive index, that it has real and imaginary part. And this plot is then representing how the refractive index, real and imaginary parts, are changing if we change the chemical potential. So chemical potential, as I mentioned, can be changed by applying different voltages to the graphene modulator in this case. So we can see that if we imagine here is a 0 and 1 state, you see that the difference is quite high. So we see that the amplitude can be changed dramatically by changing the refractive index. For the phase modulation, it's the same. So we are modulating the real part, and we see that the changes, if the Fermi energy is shifted higher, can be modulated also in a decent range. So certainly this is valid only for certain wavelength, and the TE mode in this case, for example, is simulated, but this shows the potential of the graphene and explains the effect how the graphene can be absorbing or transparent in both cases. Very important remark here is to understand that this change between 0 and 1 state in this particular case is strongly dependent on the graphene quality. Yeah? So here is the literature report by showing how graphene quality is changing the modulation depth, in this case we can call it, or absorption rate. So it depends on the graphene quality, and this is shown by so-called scattering time in graphene. So scattering time means that the charge carriers can fly without having any collision. So the higher the scattering time we have, the better the performance of the refracting index change. So this is the basic of this graphene light interaction, and certainly this effect allows us to create various concepts with graphene modulators. So to summarize, we have, as I showed a couple of slides before, broad optical response. We can change the wavelength from visible to the infrared, and we still have this effect. Graphene, as I just showed, had a strong interaction with the light. It means we can reduce the footprint. We can tune the Fermi level or the chemical potential by applying the gating. Graphene is CMOS compatible, it's just carbon, and ideally we can lower the power consumption in this case. With this, I would like to introduce you which kind of modulator, what types of modulators exist. Yes, so first one, let's start with the very simplest approach. We have single layer of graphene and we have silicon waveguide. So you can see in this illustration, graphene is placed on top of the waveguide. You see in this case, green is a doped silicon. You are making the capacitor with the doped silicon. You have one contact here and one contact there. So you're building the capacitor between graphene and your doped waveguide. In this case, the process is slightly complicated because you have to work with the doped silicon, and you still have some losses due to the silicon free carriers in the waveguide material. There was a concept proposed a couple of years ago, so-called dual layer graphene. So instead of using one graphene layer, we can put two graphene layers, which are separated by the spacer, which is called the spacer layer, which is nothing else as a dielectric in between. And we are then making the capacitor between first and second graphene layer, or the bottom and the top graphene layer. So in this case, we can call it passive waveguide modulator because there is no need for the doped silicon. And in this case, the losses or the performance of the graphene of the modulator is dependent on the graphene quality and of course contact resistance only. Another concept which attracted also our attention and where we focused the most is using the silicon nitride as a waveguide material. So we take the same concept, two graphene layers separated by the spacer layer, and then we put everything on the silicon nitride waveguide. So why silicon nitride? So it's certainly refractive index is changed, we have lower losses, and we can work in a broader range of the wavelengths of interest. So this is the device which we have been following, and in the literature is also one of the most promising structure. So I explain you a little bit of the theory, why and how the graphene is good for the modulators. I want to give you some of the aspects, some of the insights, what is important to understand if we want to do the fabrication and further do measurements. So simulations are certainly playing a big role because we have not only here biases and voltages, we also have to deal with the propagation of the optical modes. So I just have here two examples to be shown. There are much more things to be considered, but here's an example of the silicon waveguide. So now it's a cross section. You can imagine silicon waveguide and a graphene on top. And in this case, we're having silicon nitride just to compare the previous slide what I showed. So you can see immediately that there is something different in both cases. So silicon, for example, has higher refractive index. Therefore, the mode is being confined much more into the waveguide. As we want to have the high interaction with graphene, we want to spread the evanescence field out of the waveguide. Yes, that the light graphene interaction gets higher. So in this case, with silicon nitride, we can do much more and have the higher optical mode interaction with graphene. So it's only one thing you have to consider before doing your devices. There are certainly types of modulators. We can speak about the straight ones. I will show in a couple of slides some details. We can enhance, let's say, the coupling by introducing the ring structures into graphene. Then there is much more to be considered, yes, before you do the full cycle of simulations, fabrication, and measurement. So I wanted just to mention that you have to be very careful by choosing the materials. Waveguide design has to be adapted, and people have to understand the coupling efficiency. It's very important the way the light is being coupled in the so-called grating coupler. More information I'm going to show, which type of applications you are interested, and many, many, many other considerations, what we call in the designing of your graphene photonic devices. So let's start with a couple of examples which play a role and what should be considered by making the graphene modulator. So first of all, as I mentioned, we need to couple the light in. So this is a top view now of the modulator, simplified version. So you have so-called grating coupler, and this is a cross-section of this grating coupler. You have to couple somehow the light in, so you must understand the details of the coupling efficiency and so on. You have to adjust the process flows for etching, for example, these tubes down. You have to understand the pitch and many other parameters. So I want to show a small illustration here how the simulations could be done. And basically we are shining the light with a specific angle in 14 degrees in this case for the specific wavelength. In this case is the C-band, and we can see the way the light traveled through the grating coupler and now is propagating through the waveguide to the active area of the modulation. So very important aspect is to design your grating couplers in a way that they work in a specific wavelength and have the specific coupling properties. If we go now to the modulator itself, here are a couple of examples what people have been doing and what's important in designing the straight modulator. So straight modulator is, as I showed in the previous slide, grating coupler. You have a straight modulation area, and then you have light coupling in. So you have to understand, and you have to focus on, for example, the spacer layer thickness. Yes, here is shown, for example, if we change the spacer layer from 15 to 30 nanometers, we completely change the picture of the modulation depth and the voltages that have to be applied and further effects. On the other hand, there were some reports, for example, that the slot waveguides are being used, and the slot waveguides are used in order to enhance the field localization. You can confine the mode between the two waveguides in the slot form, and therefore enhance the properties of your light coupling, and then certainly the graphene modulator itself. The important aspect I wanted to show here with the straight modulator is the modulation depth. So basically the modulation depth is defined by the lowest and the highest state, what I showed in the refractive index change. It's still around 0.2 dB per micrometer. So one way to increase the modulation depth is to use so-called ring resonators, and the ring resonators are certainly of interest, but more details have to be taken into consideration. First thing is so-called critical coupling. Yeah? So critical coupling is basically defined by the coupling loss between the bus, this is the bus waveguide, and the resonator. So they must match, or in other words, we can understand that the critical coupling occurs when the rate at which the light is being coupled into the ring is equal to the rate at which the light is being dissipated, yes, due to intrinsic losses. So whenever we put graphene, we are increasing the losses of the ring resonator itself. So therefore, designing and understanding the critical coupling is very important. So alpha is defined by the losses in the ring itself, and we can see with this a small simulation illustration, how do we change the total transmission. Total transmission is T, which means light in, light out. And how does it change if we are changing the alpha? Yes, alpha, once again, is the parameter which defines the losses in the ring. So we can see that at a certain point, our transmission, our T, is becoming 0. It means that graphene is absorbing in our case. But if we still increase our alpha, we can see that we are changing it back to the T equals 1, which means that graphene is becoming transparent in this case, and we can have the high modulation just by small changes. I just want to illustrate it once again with the simulation picture, light in, light out. And if we have no graphene, we are in critical coupling condition. We are basically sending the light in, and it's being coupled into the ring, but still the total output is then defined by the bus waveguide. So in this case, if we put graphene, it's just an illustration. If we have graphene, we can see that graphene is absorbing and much less light is being sent through the bus waveguide. So we can actually modulate the light by adding graphene to the ring. It's also very important to understand this critical coupling, because it's also changing another parameter, which is called extinction ratio, and is defined by the minimum and maximum position of your transmission dip. So if we don't have any graphene, we can design our ring resonator in such a way that it's in a critical coupling condition. And once we put graphene, it is starting to absorb. So we are reducing the extinction ratio. As long as we are biasing graphene, which is shown in this example as well, we can go back to the critical coupling conditions because graphene is becoming transparent in this case. So you can see here the experimental result, how applied voltage to the graphene modulator is changing basically the modulation depth, yes, or the transmission, in other words. So as I showed you in 2 slides before, with the straight modulators, we are at around 0.2 dB. It's just a number for the reference, and in this case, we can increase significantly the modulation depth. Certainly, there are furthermore parameters which have to be discussed, but just to illustrate the importance of the ring resonators is demonstrated with these couple of illustrations. So these are the fabricated devices, how they look in reality. Basically, the straight ones is just a waveguide with the active graphene area. In the ring case, the ring is demonstrated here. And with the Mach-Zehnder modulators, which I did not present in detail, are also fabricated and are given as an example in this picture. So to summarize the modulator part, this is the state-of-the-art result of the graphene modulator, which has a rather high complexity of integration. So you can see here that each graphene layer, so the top and bottom graphene layers, they are incorporated with hexagonal boron nitride, which is needed, let's say, to shield graphene from the environment. The authors also put hafnium oxide as a high K material as a spacer layer in order to increase the capacitance, and they reached the 3 dB bandwidth of around 40 gigahertz. So this is, so far to my knowledge, is the record value which was demonstrated. And this plot basically summarizes the potential and application as graphene for the modulator for the high speed operation. So on this axis, we see if we increase the mobility, we directly increase the bandwidth. Certainly, there is also the RC component involved, and we have to optimize the contact resistivity. And if we reduce the contact resistivity from 1.7 kilo ohms to 500 ohms micrometer, and we have decent mobility of graphene, we can really reach very high speeds of the modulation of 3 dB bandwidth, and we can be very, very competitive with the state-of-the-art silicon modulators. Okay, so this was the introduction of the graphene modulators and graphene for photonic applications. I hope I showed you a couple of details why graphene is good for that and what state of the art. In the second part of my talk, I would like to focus a little bit on the experimental MPW run, which we are going to provide and offer. So this is the basic building block. Don't understand it that this is the final device. I just want that people understand the basic idea of the concept of this MPW run. So we have the standard silicon substrate, we have the bottom cladding layer, and we have silicon nitride as a waveguide material. We put one layer or two layers of graphene, and then we can realize contact to this both graphene layers, which is then covered by the top cladding silicon oxide. So here are more specific already device architectures that we could think of. Certainly it does not mean that we can do them in one run, and that if it's possible at all to do many of these concepts, but let me group a little bit them. If we speak about the optical, let's say, modulation with other light source, so you don't need the contacts, you can have so-called passive graphene modulators, where waveguide is formed and you have a graphene layer on top and then covered with the passivation layer and the top cladding. It will also have an option to have the metal heaters if you want to induce any heating effects to your devices. In this middle picture, we demonstrate that graphene can be put on the waveguide if there are device concepts that require contacting one graphene layer, we could do graphene contacting from the top. The most advanced one and the most complicated at the same time is so-called this dual layer graphene, what I just showed in a couple of slides previously, will be done with the bottom contacting, and then I will show in the next slide a little bit more details about that. So two graphene layers separated by the spacer, and the contacts are done from the bottom. I would like to give some details about the flow. It's listed the step by step here, and I will try to show the illustrations, certainly the fabrication steps. So I mentioned we are starting with the standard silicon wafers, and we can put bottom cladding of silicon oxide in the range of 500 nanometers to 3 micrometers. So if your design requires 1.2 or 1.6 micrometers, it's realizable. The silicon nitride waveguide material, which I mentioned, is maximum limited to 500. Our most experienced and most advanced state is 400 nanometers. You could keep it in mind if you are interested in the experiences and the properties that we have already. So in the next step, we have to apply lithography step, and we have to form grating couplers and the waveguide itself, what I mentioned. Small illustration of the grating coupler that can be done if you use, as I mentioned in our case, 400 nanometers, and if you etch half of that in and your period is around 1 micrometer, you could expect a losses per grating coupler of around 6 dBs. So this is our experience, what we have, but certainly different design of grating couplers can be realized. Then we are putting on top of this waveguide material another silicon oxide layer, and we do so-called chemical mechanical polishing, where where silicon nitride is then embedded and has a flat surface of the silicon oxide and silicon nitride in combination. As we did that, you see that we are using graphene grown on germanium process. I'm not going to details in here. So we are transferring the first graphene layer, which is done also in-house. And just as a reference, you could take away these values. We have the sheet resistance of around 1.5 kilo ohms per square, and our mobility is around 1000 after transferring the graphene. So first graphene is done. We are patterning it in the dimensions and the shapes you would like. And then we are putting the spacer layer and do the same step with the second graphene layer, which is followed by another passivation layer. We, of course, have to cover everything with a top cladding layer, and the top cladding layer is, again, we could realize some structures within the range of 500 to 3 micrometers of silicon oxide. As for the contacts, as I mentioned, we have different approaches depending on the designs and on the needs. If we do the bottom contacting approach, we are around 2.1 kilo ohm micrometer, and if we are using the top contact approach for single layer graphene, we could go as low as 300 ohms micrometer. So these are just key values to take away in case any designs are being done. In the very last few slides, I would like to show the details of the PDK. PDK stands for the Process Design Kit. And as I mentioned in the very first slide, at IHP, we are offering more advanced and more qualified technologies, and they all have the PDK and so on and so on. So we try to do with the graphene the very basic first steps in order to help the designers to fully understand our process capabilities. So we have layer table, we have DRC check, and we have the first P-cells and scripts for the filler generation, for example. So let me give you a very few details. I don't want to bother you with many of the technical stuff. So in case of interest, we will provide the initial document with the layout rules. Each layer that will be used in this experimental run is listed and will be provided to you. So you have to use the layer table as in the standard technologies, what you might know. And the design rules are also given with the minimum spacings and so on and so on. What you would have to do is to draw the seal ring, meaning that you have to frame and put all of your designs inside this frame. And this is available in Texeda as a P-cell. And we are working now to provide this IHP graphene PDK in the K layout as soon as possible. So once you draw this seal ring, you are free to draw your structures. Two things you have to consider is that the waveguide fabrication and the metals fabrication requires the fillers. Here is the example of the metal. So you see this box is just our metal material, and then you have to generate the fillers around. You see everywhere is nicely generated except the area that we have to avoid. The same is applied for the waveguides, and we see that this is the waveguide now box drawn, and if we generate the fillers, everywhere else is generated except the area that is not needed to be processed. I will certainly provide more details in case of interest, but this is just the basic information what we are offering or what we so far have developed for this experimental run. DRC check is certainly a very important aspect because we want to get and receive the GDS files which are clean. So here's an example of shown of violated DRC check. You see the contact pad, you see the active area, and you see that the contacts are drawn in the wrong place, and you are violating the minimum rule, for example, of the distance to the edge, and the DRC check will basically give you this information that you have time to correct these issues. Once again, it's already available in Texeda, and then will be available soon in the K layout. Okay, so with this, I'm coming to my last slide with some details. If you are interested, feel free to contact us. There is also in the 2D EPL or Graphene flagship website the link. You can directly write to us, and we hope that Europractice access will also be organized soon. And the dates to remember is the 14th of October. So you have time until the 14th of October, which is the hard deadline. I encourage, if any of the interest, to contact us as soon as possible to discuss all the details. You have to sign an NDA, and we certainly have to understand your needs, and we have to see if we can realize your exact designs. Okay, with this, I would like to thank the audience, and here are my contact details. Feel free to contact me at any time.